castle where the digital dreams come alive. CESCG takes place from May 1 to 5, from visualization to the virtual space. Scientific sessions take their place.
Hello everybody. As already said, my name is Matyáš Kovaľ. I come from CTU in Prague, and I'm going to talk to you about acquisition of cognitive maps by individuals with vision impairments using virtual reality. Now, that is quite a mouthful, so I'm going to start us with a funny picture. Or not. Because I think all of us have a house or an apartment that we know like the back of our hands. We know it quite well. You can even orientate in it at night, I guess. That is until somebody goes and moves something around. Then you completely lose your touch with your surroundings and start going into things. And that's where the issues start. Now, this may seem like an oversimplification, but imagine that you cannot turn on the light. And now, instead of somebody moving something around, you are in a completely different space or environment. Well, that is how visually impaired people can feel, for example, which is something we wanted to address. Now, a cognitive map is precisely your idea of your house or home. It's the mental image of the plan of it, or directions you have to take when you want to get somewhere. It can have many different forms, but in general, a good cognitive map is connected with your own safety because you know how to navigate your environment without running into things. A virtual reality may seem like a strange choice for visually impaired people because I guess for most of us, visual reality represents the visual image. You have the headset on your head, and you see a different reality through it. Now, that is not the main feedback we are going to use, and it's not the main purpose, because virtual reality means virtually simulating some feedback that the user can react to, which can, of course, mean even haptics or even auditory sense. So, for example, as illustrated in the pictures, there are many different ways how to use virtual reality and not use the visual feedback that we are used to. So overall, we want to utilize virtual reality to help people who have vision impairments create a cognitive map, and now we understand what this goal entails. Well, we were not the first to delve into this problematic, so first we did our research to figure out the current state of the art. We found a few articles, but the main of those were articles by Kunz et al., who mainly focused on using purely auditory feedback to help people create cognitive maps, and Siu et al., who went so far so as to create a whole new virtual cane that was connected with servomotors that actually stopped according to the virtual reality and allowed the user to explore his surroundings. Now, this work was our main inspiration, you could say. Overall, we tried to connect all the information we found and utilize it. Now, we had to decide on what to use in our project. And we saw what Siu et al. Had to go through with creating the whole new different white cane, and we wanted to simplify it, or simplify it as much as we could. So we thought about connecting the virtual white cane to a virtual reality controller and utilizing the headset for the rest of the tracking, which is what we did after some more research into what headsets to use. Now, this right here is the first prototype that we created. It's just an attachment of a virtual reality controller to the white cane. Now, this controller only has haptic feedback. It can provide vibrations which go through the white cane into the user's hand, and he can react to them. Now, we had to figure out where to test this, because we've had some feedback for the user, but he had nowhere to try it. So we created a really simple empty room with a nook and a pillar in it, where we could do our first testing of the prototype and figure out if the basic mechanics work. Unfortunately, due to real space limitations, we had to settle down for only the nook, because even this part of the room is about 3 by 3 meters So even this required quite a lot of real empty space, which was safe for the user to navigate, which was the main thing. We really tried to make the participants safe and try to explore their surroundings in the most safe way possible. Now, the test itself, we had to try to verify the basic principles of navigating a white cane, and among those is movement around guiding lines, which means finding a guiding line, either artificial or natural, for example, a wall, and going around it or with it. The procedure was quite simple. We only took our participant, put him into the virtual reality environment I showed on the previous slide. They were free to explore, find the first guiding line they were able to, and walk along it. And the evaluation was done qualitatively, so by the observation of the supervisors and gathering feedback from the user himself. Now, this is a showcase of how it could look, for example. The user moves the white cane, which is tracked in the virtual environment. Each impact is collected and makes vibrations directly in the cane for the user to feel. The results were quite optimistic because the participant was quite quickly able to find the guiding lines that were around him, walk along them, but we've also started to run into some issues. The first of them was the fact that the user had access to the surrounding sounds. So at first, he heard my laptop, which was used for playing the virtual environment. So he heard it and was able to pinpoint his location according to the laptop. So he always knew which way he was facing, which was unintentional, but quite helpful to him. Also, we found out that all the spaces that the user found, the empty spaces, seemed smaller than they actually were. So, for example, if you remember the space between the pillar and the wall, the user determined that it was not possible to walk through this space. Now, this was the point at which we started writing the article, but since then, we were able to make some improvements and do a second round of testing. We've also improved on the virtual environment, and we've moved it as close as possible to a real environment we've got at our university. We tried to make a model out of it, and this is the overview of the whole model that the user was navigating in the second round. Now, the procedure changed a little bit, because since the environment was more complicated, the task got more complicated as well. He had to navigate through the environment. He started in the halls over here and had to move to this room, find an object in the middle of it, and move out and to the toilets next to the room. Now, the evaluation was done the same way as before, and the user also had access to a tactile map, which is shown in this picture right here, because we wanted to try to find as many possible ways to provide the user with information about his environment so he would feel as safe as possible and had the best cognitive map he was able to create. Now, the thoughts behind this might have been good, but the results were mixed because this testing round included a lot more participants than the first one. And we quite quickly found out that every user that engaged in our testing was different because most users were late blind, but the amount of time that they were blind differed. There were also congenitally blind people who are blind since birth. So we found out that every user had a different approach to using the white cane and relied on different senses to orientate themselves. And we were, in some cases, not able to provide them with everything they were used to, which was one of our goals as well, to make it feel as natural to them as their normal approach to orienting themselves. There was also an issue that when the user got lost, they had no way to reset themselves except for the supervisor stepping in and putting them back in some starting place where they knew they were, where they could continue from again. And also we found out that since we limited their real senses, we were not able to fully supplement them by virtual senses. For example, when we put headphones on a user who was more used to using echolocation, the user was quite confused. Now, those were the results of the work so far. I would like to thank all the authors of the articles we have used and who are inspiration to us. And overall, all the things I've mentioned that were wrong or we found out as issues are things that we have to handle in future development because they were all real feedback for us and they were all things we have to take into account if we want to provide the virtually impaired individuals with a safe way to use virtual reality to create a cognitive map. Thank you very much.
So thank you for the presentation. Do you have any question? Yes.
Thank you for a very interesting presentation. Can you tell us more about the structure of the participants? Were all of them completely blind, or did they have any other visual impairments, any other disabilities? And how did they react to this solo environment? Because you mentioned that you had a tangible model that was shown to them. So was there a difference when you used only one method or other methods? And what were their exact thoughts on the system that was used? Thank you.
First, I'll start with the question about vision. There it was mixed. Everything was mixed because we've had, most of our users were completely blind, but there were also users who were used to using the remains of their vision to orientate themselves in well-lit rooms. And these users surprisingly performed better because they didn't have the sense they were used to, so they paid more attention to handling the white cane, and they paid more attention to the feedback from the white cane. As for the tactile map, the testing was done mixed both for the tactile map and for the virtual environment, and the only thing we switched was if the tactile environment was provided first or second. And the users agreed that the tactile map is good for getting the orientation of the layout of the greater space, but the virtual environment was usually better for specific obstacles, for example, chairs, tables, etc., which would in the tactile map be too small to notice or difficult to identify.
Thank you very much.
Thank you.
Very nice work. So I have several questions, but I'll just ask one. Did it occur to you that you could use the 3D map that the headset is creating for, conveying the boundaries of the space? Because you had to hand model the environment, but you get a point cloud from a headset like Quest 3 or Quest 2 that you used.
It hadn't occurred to me before, but thank you very much for the feedback, and I'll be sure to consider it in future development because it sounds like quite a good idea.
Thanks.
So I have a question. How many users use your technology?
The first prototype testing was only done on a single user and users who were not blind but blindfolded. And the second testing was intended to be done by 6 to 8 users, but unfortunately, due to the users not arriving or not responding, we only had 4.
You said that one of the problems was that when people got lost, somebody had to take them and move them back to the location that could be actually used. Have you considered using the tracking capabilities of the headset to navigate the user back, for example, through audio and spatial feedback, saying, okay, take 2 steps back, and now you're in a location that you know that you haven't visited before?
In short, yes. We've considered many different approaches to this. This was one of them, but we will try to combine multiple simpler approaches, for example, labeling all of the parts of the path they can take or the rooms, and giving them an audio anchor that will stay in the same place and will be on demand, that they will be able to use to orientate themselves in the directional case, and then they can use the feedback about what room they are in and whether they are inside of an object or not to move outside, so at least they will be able to get to free space that they will know where they are and start again from there.
Okay, so thank you.
Swing to the beach where the pixels play, from rendering to VR. It's a pixel away.